Hi, so I'm Gene and this is Dean, and we're going to talk to you about rocket-fueled cars. Today we're going to talk about why we want to change from today's cars, in particular hydrogen-fueled cars, where we can get hydrogen from, how we can store it on a car, a world distance record that we broke at the laboratory just recently, and then the bigger picture of hydrogen fuel around the country and the world. So first, let's do a warm-up exercise and figure out how much energy it took for all of us to get here and to go home again today. Cars use a lot of energy continuously. So how many of you have come from less than 10 miles away? Raise your hand. Okay. How many from 10 to 20? Okay, not many. And how many from 20 or more? Yeah, me too. All right. How many miles a gallon did the vehicles you come in get? Less than 15? SUV? Truck? Okay. 15 to 25? Most cars. Okay. More than 25? Some fraction. And how many people here have ridden a hybrid car? Okay. Well, on the average in the U.S., cars get about 20 miles a gallon. And I think here it looks like we averaged about 20 miles to get here. All of us today, there's about 600 people. That'll be enough energy for 10,000 hot showers. So we better make good use of this meeting. Driving accounts for nearly a fifth of all the energy in the country. This is a flow chart showing basically how thick these lines are, how much energy we use for different things. This is all the oil the country uses, and this is all the oil that we use for cars. So it's the single biggest use of energy, and by far the single biggest use of oil. Where does our gasoline come from? Oil we find in the ground. We don't make it, we find it. A lot of it's found in the Middle East, far away, and shipped thousands of miles around the world with traffic jams of supertankers to run our traffic jams of cars. We go to pretty extreme places to find oil, exploring in deserts, exploring in the Arctic, in Alaska where I grew up. I grew up here, and when I was born, Alaska discovered oil up here, and this was the single biggest find of oil in the country's history. And took them until I got into elementary school to build this pipeline. It's 800 miles long, shipping 2 million barrels of oil a day. By the time I was your age. And now, instead of 1 out of every 8 gallons of gasoline that it used to provide, to California mostly, it's only 1 out of every 25. And this is probably the last best oil reserve in the United States. So oil is going to be a dwindling resource in the future, and yet we're going to use more and more cars driving farther and farther, probably. Only 1 in 10 people in the world have cars today, and they all want more. So what can we do? Well, we can try to be efficient and drive more efficient vehicles, some hybrids or smaller cars. You could switch fuels from gasoline to natural gas. The possibility of electric cars. There's the EV1 from the 90s and the new Tesla Motors car that they're selling today, actually. And hydrogen cars I'm going to tell you about. This is an experimental car from Ford. And this is BMW's latest hydrogen car that they're actually going to make 100 of and let real people drive, at least real famous people. Then I'm going to talk to you about where we can get hydrogen. First of all, a little bit about what hydrogen is, probably. Here's your periodic table of the elements. Hydrogen's the lightest element. Just a single proton and a single electron orbiting it. Very small, very simple. It's a gas at room temperature because it's so light. And the word hydrogen, hydro in gen, means water former. So where can we find hydrogen then? In water. Water is H2O, of course, we all know. And here's your water molecule. Basically, the oxygen steals most of the electrons from the hydrogen atoms, so it has a negative charge, and the hydrogen atoms are left with a positive charge. So you've got this water molecule. How do you want to get hydrogen out of it? Any ideas? Yeah? Put energy in. What kind of energy? Any ideas? Yeah? Very good. So you can put a charge here, and a charge here, and now these charges will be attracted here, and this will be attracted here, and you can pull the atom apart, or the molecule apart to separate atoms. And we're going to demonstrate that now.
Okay. What we have here is an electrolyzer. And basically, it's just equipment to do electrolysis, like Gene was saying. And so inside these columns is just water. Water, again, is H2O. And what we want to do is we want to separate the water down here. And we can do this by providing positive and negative charge on different sides here. So if I put a positive side with this red cable here, and supply positive charge here, and supply negative charge over at this black end, I can get, just kind of like, you guys know how magnets work, right? You take a red magnet, which side of what does it want to attract to? If you have let's say, okay, let me make it easy. You take a red and a black magnet, okay, and put them together. They want to attract, right? And you take a red and a red, and what happens there? They repel. Good. So if we can go ahead and create charge, kind of like a magnet, we can get the negative oxygens pulled to the positive side, and get the positive hydrogens pulled to the negative side, and start separating water molecules. Okay, so let's see if we can do that. Okay, so I put the positive lead in, the negative lead in. I'm going to turn on my power supply. Okay, nothing's happening. Now I'm going to go ahead and start increasing the voltage, which helps create that force to push these charges. And we see bubbles. And I want to see more bubbles. That's pretty good. Okay. Now, the way a water molecule is set up is it's H2O. Every time water splits, how many hydrogens are you going to get? 2, and how many oxygens are you going to get? 1, right? So which column do you think is going to go ahead and fill up first, the hydrogen side or the oxygen side? The hydrogen side, and should be an exact 2-to-1 ratio. Okay? I'm going to go ahead and set up electrolysis down here, because this is on a timer, so let me set this up. And the on switch is right here. Okay? And now we can kind of see that the hydrogen the hydrogen gas has filled up this column a lot more than the oxygen, and they were at even levels before, and so we're successfully creating hydrogen and oxygen right now just from water. Okay?
Okay, so we'll have some questions for electrolysis again. How much more hydrogen than oxygen did we make? H2O, 2-to-1, right? And where did the electric energy go? Any ideas? We put energy in. It went into pulling the hydrogen and oxygen apart. So how can we get that energy back? Any ideas? Combine them. Particular way you want to combine them with a spark would be good, flames, right? That's indeed how we use hydrogen today. The only use of hydrogen as a fuel, really, right now is in the space shuttle, with a big hydrogen, liquid oxygen tank. Out here's where they fill up, and the space shuttle's main engines work that way. So we've got a small hydrogen rocket here today, over here, where we're making fuel by electrolysis. And here, hopefully, we can see bubbles. And then we'll get a countdown going. So let's see here.
So as those bubbles are starting to form, you probably can see those down there at the bottom. That you're getting twice as much hydrogen as oxygen. It's filling up there. What I have in my hand is a little trigger, and when I press this button, it's got to create enough hydrogen and oxygen, enough fuel to actually cause the rocket to go. So that's why we have a little timer system here. And what we're going to do is when I hear a beep, which tells me there's enough hydrogen and oxygen in there, we're going to do a countdown. And so I'd like you to just go ahead, and we're going to start with 5 because I only have about 10 seconds to press the button, okay? So when we hear the beep, we'll be ready for launch, and then we'll count down and see what this does.
And we'll cross our fingers. Not all rocket launches go as planned. Oh, there we go. That's a lot of fuel.
Okay, ready? 5, 4, 3, 2, 1.
Oh, very good. Wow, very good. So now we've shown how you can use hydrogen in a rocket. We like to use hydrogen in a car, and it seems like we've got the burning part pretty much under control. Storing hydrogen, however, is a little harder, and that's what we're going to talk about for the rest of today, is how to store enough hydrogen on this car. There's basically two ways to store hydrogen. You can see that took a nice big tank at the bottom of the rocket. The space shuttle has a huge tank for the shuttle. Your car needs a much smaller tank, a big car, hopefully. So we can squeeze hydrogen molecules together, really, really tight, really, really compact, as a gas, or we can cool them down until they lose all their energy and stick together and make a liquid. So we're going to first talk about squeezing hydrogen. This is a very strong pressure vessel where we can squeeze hydrogen to 1/300th of its normal size. The walls of this tank can hold 5,000 pounds for every square inch of area on the wall. I don't know quite how hard to say what that is, but it's a lot. Here's these hydrogen molecules all banging against it at 5,000 pounds per square inch. There's a lot of square inches, and that means that all those molecules together are pushing on that tank with 10 million pounds. So this tank here can hold up 10 million pounds. That's a lot of people. It's probably more people than are in these cities, and it's enough weight to hold up 10 space shuttles in your car. So you do all this to squeeze down the hydrogen as much as you possibly can, get as much fuel in your car as you can, with a tank that's about as big as you'd want. Put it here in your trunk. So how far can you drive on 10 million pounds? Well, in that tank we can hold 4 kilograms of hydrogen gas. And just to make one thing easy in class, a kilogram of hydrogen is equal to about a gallon of gasoline with the same energy of fuel. So this tank stores about 4 gallons of gasoline equivalent hydrogen. And if you have a car that goes 50 miles a gallon, should be a pretty good hybrid car, you can get about 200 miles, which is enough to get around, longer than a battery car. You could quickly refuel it. But what if you want to go farther? Well, the space shuttle goes farther. So we'll try putting rocket fuel in here and talk to you about that later today. Rocket fuel is liquid hydrogen. I'm going to give a little idea of how cold liquid hydrogen is. Here's California, 70 degrees. Here's where I grew up in Alaska, 0 degrees. Here's the coldest place on Earth, Antarctica, minus 70 degrees. And there's liquid hydrogen at minus 423 degrees. So we're going to give you just a little bit how cold this is. Reese will show you liquid nitrogen, pretty close to liquid hydrogen.
Okay, this stuff is really cold, so I need to use some gloves and some goggles to protect myself. And so what I'm going to do is take out one of these tanks here that's holding, again, this stuff is just a few degrees hotter than the coldest the universe can get. So it's just a few degrees above absolute zero, okay? And we'll just go ahead and pour some of this in here. And we'll continue to pour some of this in here. That should be good. Okay. All right, now if you take a look at this, you see a lot of kind of like evaporation happening, the liquid's turning into a gas, and it looks like boiling. And when you think about boiling, you think of like hot substances, okay? This is liquid nitrogen, and it turns out that the atmosphere is mostly made out of nitrogen, mostly composed of nitrogen, about 80%. So this is kind of like liquid air. So at room temperature, what state of matter is air in? It's a gas. How can you take a gas and turn it into a liquid like we have here? You got to cool it, and you got to cool it down a lot, okay? So I want to prove to you this is cold. Okay, so what I'm going to do here is I have some water. I'll prove that it's water. It's pretty good too. Okay, it's tough with these big gloves. Now I'm going to add some water to this larger bottle. That's good. I'm going to take this and I'm going to put it in the liquid nitrogen, and we're going to see what happens here. The liquid nitrogen is actually starting to boil even more rapidly than before. It's taking the heat that's in the water and allowing that phase change to happen, so it goes from that liquid to a gas, evaporation. You can hear crackling. What do you think that crackling sound is? Water turning to ice. Good. Now, if you were to go ahead and do this at home in the freezer and take water and pour it into an ice tray, how long would it take for the water to turn into an ice then? About an hour. We're doing that in about 30 seconds right up here. So this stuff is really cold, okay? Just so you know. Okay. And so we have frozen water. And a little bit of water that's left, and the rest of it, there we go, is frozen at the bottom, or now at the top of that bottle. Okay, so let's kind of look at another aspect of this process. Let's see, I'm going to add a little bit. Take this cup, take this metal.
A balloon?
Oh, you want to do the balloon? Okay, we can do balloon first. Either way. Let's go ahead. All right, check this out. What's inside this balloon? Yeah, because it's not floating, right? So this is just a regular air-filled balloon. Let me go ahead and take this, put it in a space so I can put it in here and watch what happens. Ooh, I love my job. Okay. There's no leak in the balloon, yet as you can see, when the air inside the balloon got colder, what happened to it? It shrinks, it compresses. We got a twist there, woo. Now, in that short amount of time, the air just heated back up, and then what happened to the air as the balloon got warmer again? It expanded. So that's a big property with gases. You cool them, they get small. You heat them, they expand. You guys want to say that one more time? That's what I thought. So let me go ahead and put these in. Okay. Again, it literally takes the air and squeezes it and squeezes it and squeezes it, and it just, from the cooling process, it takes up so much less space. And here we go again. Okay? So that shows you how gases can expand and compress when they're heated and cooled. All right. I'm going to do another quick demo here. Have this cup. Sure. I'm going to go ahead and fill it up with liquid nitrogen.
Whoa.
Okay. So you can really see it boiling well here, and very rapidly. And what I want to do is start to show you kind of like how the hydrogen would behave inside that tank, okay? If we let that tank get warm, because the only way we're going to get hydrogen, enough hydrogen, kilograms of hydrogen into that tank is by compressing it and by cooling it. Turns out that if you have one drop of gasoline, just one little droplet, that's about the same amount of energy that you'd get out of all of this hydrogen inside this balloon. A drop of gasoline doesn't get you very far. Right? A drop of gasoline gets you about 6 inches. That's probably not going to make you commute to work or to school or whatever, right? So what can you do instead? We cool it down, and we need to keep it cold so it stays compressed, and so the tank helps to compress it, but we need to insulate the tank and make sure there's no heat that's leaving the liquid hydrogen in the tank. So let me show you, when I take this cup and place it on this conductor here, which really is just a metal that can take heat from the air and bring it up through the cup, you can see it really wants to boil vigorously. A lot of heat is going in, and so we get a lot of liquid turning into a gas. If I go ahead and take this cup and lift it up, It got quiet. It's getting quiet. What's happening?
Staying cold.
Let's try this again. Ready? Put it on the metal. The noise that you're hearing is what? Boiling. Go ahead and take it up. It's not boiling, okay? If it's not boiling, that means that it's not absorbing as much heat to go ahead and turn that liquid into a gas, right? And so one thing that we want to do with the tank is make sure that there's as little bit of contact as possible surrounding this chamber right here. We want to that's what these spacers do. They provide a little space so that there's not much contact with other solids to the tank. Okay? Thermos time. Okay. So, what we have here?
Helium time.
What's that?
Helium.
Okay. Oh, you want to do the...
Yeah.
You want, okay. I'm out of order. All right.
It's okay.
Let's see. Let's take this balloon here. And we need to fill up the tin.
I can do the filling.
Okay. What's different about these two balloons? Yes? One's filled with hydrogen, one's filled... They're actually filled both with helium, okay? Filling a balloon with hydrogen is a little bit dangerous because it's an explosive gas, right? It can ignite. So they're both filled with helium, or else I'd probably be wearing some sort of like face shield right now. And what's different about them is, if you notice, look at the kind of shiny reflective coating on this balloon. This one's a lot darker. Does anybody know what properties dark things have that's different than, let's say, these reflective ones? I see over here, yeah. Anybody? This can absorb a lot more heat, and this is going to reflect heat. And the type of heat we're talking about here is heat that can come from light and other sources of like radiation, right? Like infrared heat waves. And so reflective materials can really reflect heat waves easily. So what we're going to do is we're going to take both these balloons, submerge them again in the liquid nitrogen, get them real cold, and then we're going to go ahead and toss them out onto the stage right here. Don't worry, front row, you guys will be okay. And we're going to go ahead and see which balloon races to the top first. And does anybody have a hypothesis? The black one, why would the black one get there first? It's going to absorb more heat. If it absorbs more heat, it's going to fill up more, and big balloons float faster than balloons that are only filled up a little bit, right? So we'll see if this works. We'll see if reflective coating really makes a difference.
Let them cook for a while.
It's like a cooking show. I feel like I should be basting something.
It's cold.
Okay. You ready? One.
Let's give it a few seconds to
Okay.
settle.
Do we want to put the weights on the other side first?
Oh, that's right. Yep.
Okay.
Okay.
Ready? 1, 2, 3.
And we'll see what happens.
Ooh. Okay. So that's a
There you
pretty
go.
good illustration that darker balloon is absorbing more heat, which is going to expand the air. Remember, heat expands air, and it's going to make it more buoyant, and it starts floating up. Okay? One more demo with this amazing liquid. All right.
There you go.
Okay, let's go ahead and take this and put it over here. Thank you. Okay. So what I have here is a thermos. And there's two things about this thermos that make it really good at keeping things the same temperature. What's the first thing you think when you see this thermos? It's shiny and reflective, right? So just like that balloon, it's going to go ahead and reflect a lot of heat. Expensive thermoses have another feature. Anybody know? It's insulated with with actual quality about it. Starts with a V. Vacuum. There's a vacuum inside here, okay? And so it's like a double-layered thermos. And so what they've done, the company has taken as many air molecules as they can out of the inside layer of this thermos so that it's not really in contact with air around it. Okay? And by not being in contact with air, heat can't radiate to the, or can't conduct to the air around, and heat gets trapped in really well. So let's go ahead and fill this up. And we can do a comparison between the one that I already have boiling away over here. Remember, it's really cold even though it's boiling. Okay. So let me fill this one up again. Okay. And let me fill this one up. This is a little bit trickier. It's a big thermos. This tank's heavy. I'm starting to sweat. Okay, here we go. We got it filled to the brim now. And what we can do is we can kind of look at the liquid nitrogen inside the insulated, vacuum-sealed thermos that also has the reflective coating, and then your regular everyday plastic cup. Okay? And as you can see, this cup right here, if you can see it, maybe I need a little more liquid nitrogen for our angle here. Whew. That's okay. So you can see it boiling over the brim a little bit, right? And over here on this thermos, pretty stable, not very much smoke coming off the top. It's not really smoke, right? It's the liquid turning into a gas. And so this shows you that this container is much better at keeping things the same temperature than this regular old cup. This cup is for drinking. This thermos is for keeping things the same temperature, for insulating. Okay? So if we can review, there's 3 things that I want you to know about the tank and about just keeping things cold in general. Okay? The first one is you don't want contact. That's what those spacers do. They remove the contact from the outside container, the car, anything on the outside from actually touching the tank. The second thing you want to do is use a reflective coating. That's what these layers are. There's actually 31 layers of reflective coating that prevent light waves from hitting this and warming it up. And lastly, we want a vacuum. If there's a vacuum seal, it's going to maintain a good insulation for the tank. Okay?
Okay. And so these are those basic principles here, and an example of the tank here, are what we put on our actual tank in the car outside. We took our very strong tank that could hold hydrogen at 5,000 pounds per square inch, 10 million pounds of total force, make it as shiny as we know how, have little spacers so that nothing touches the tank very much, as little as possible, only a couple of square inches on the whole tank. Put it inside a vacuum jacket here. You can kind of see the inside of the jacket here with little spacers to thermally isolate your tank. And then pump out the air. And now you've got a tank that's protected from heat in 3 ways. And that's good, because we wanted to do a bunch of safety testing on the tank, where we had to put it in a gasoline bonfire here and have it survive for 20 minutes, I believe. They went through a lot of other testing as well. Before we put it in our car, so here's the vacuum jacket you can see, hydrogen inside, and this tank here is inside that. And since it's all super cold now, I can hold not 4 kilograms of hydrogen, but 10.7. And that goes from 200 miles to 500 miles. So we did a little experiment at the lab. We want to see how far our car could go with rocket fuel in our tank. So we had a truck come by, fill us up with liquid hydrogen at 423 below zero. And then we filled up our liquid hydrogen car here for the first time. And then made a little route here. Here's where we are now, and here's where the lab is, about 5 miles away. And we drove around the lab here, like the Indy 500, for the Livermore 500. You can see a nice little route. We finished here at our building, and declared victory. And as far as we know, this car is the farthest any hydrogen car has ever gone, by a good chunk. So. Thank you. There are a lot of cars being worked on around the world, but most of them use hydrogen gas at 5,000 pounds per square inch, and that's only 200 miles. Basically, all the car companies and all the energy fuel companies are working together with the government, doing a lot of experiments, so we're not the only car. From Germany, BMW has been doing liquid hydrogen cars for a long time. This car was built basically when I started school, and this is their latest model. They'd like to use something like our tank in their next model. There's also a lot of hydrogen stations that people are experimenting with. Here's a solar-powered hydrogen station in Detroit, where they make cars. Here in Washington, D.C., so the politicians can see. And then here in California, both in L.A. and up here in the Bay. Governor Schwarzenegger has proposed a network of hydrogen stations across the state, something like 100 stations by 2010. And if you look in the future, you can kind of imagine then we could have all of these non-fossil fuel electricity sources, making electricity for your home and making electricity to make fuel, or you could even make fuel at home and have zero-emission cars, basically running off electricity, but without batteries. So when can we have these cars? Here's two models. Right now, Honda's got a concept car they think can go about 300 miles on 4 kilograms of hydrogen. Very efficient. BMW has a much faster, less efficient car that has a short range on liquid hydrogen and it holds 8 kilograms. And they're making about 100 of each of these. And we'll test drive them with real people out in the world, not scientists or car maker executives or whatever. So I think that you could probably see these by the time you graduate from college in engineering. You can ask your parents for this as a graduation present. And BMW has been nice enough to show us a little about what it might be like to fill up a hydrogen car. Whoops. So far, you just get out of your car like normal. Release your fuel switch. A little bit automated. A vacuum-insulated hose. It's really cold, right? Make sure everything's connected. Inside, you have to open a valve or two. Now this is hydrogen vapor, just like there's vapor over there, coming out of your car being recycled at the station. And this is new liquid hydrogen being put in the car to keep your car as cold as possible. So the liquid goes into this big vacuum-insulated tank that's very reflective and shiny, just like we're talking about here. And they spray it into the tank to get extra cooling. So pretty much what you can see outside in our car, see a big steel vacuum jacket, and inside it's something like this. So there's your liquid hydrogen with a little bit of vapor over. Then you decouple, and you should be ready to go. Be nice if your car knows when to close the lid. Press start, and you're on your way. So thank you for listening, and we have a hydrogen car outside for you to look at or come up and ask questions.